Good afternoon, Professor Tandon sir. Good afternoon, sir. Namaskar. I am not able to hear you, sir. I think you are on mute.
Yes.
Yes, sir.
Now I
It's a
think I'm okay.
you audible, sir. It's really a great pleasure that you have joined, sir. And in
No, no,
fact,
no.
this is our Foundation Day lecture, which
No.
we organized. So, and it's really great that now you are one among the participants. Professor Murty has just joined. Good afternoon, Professor
Yes.
Murty.
नमस्कार नमस्कार मिश्रा साहब नमस्कार टंडन साहब
Namaskar, Professor
नमस्कार
Murty.
जी जी नमस्ते
So you have got distinguished participants, sir, Professor Murthy.
जी 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 no we are grateful touched by the affection of all the colleagues who are joining
You are on mute. Mr. Ghosh, you are on mute. Mr. Ha, please unmute yourself.
Yeah.
Yes.
Good evening to all. This is M.M. Ghosh from Institute for Steel Development and Growth. We are organizing the Foundation Day special lecture by Dr. Professor C.V.R. Murty. So this is a venture. The topic of the discussion or the topic of his lecture is a journey from ductile steel to ductile steel buildings. So it will be a 1.5 hours lecture followed by a 30 minutes question and answer session. So now about Professor C.V.R. Murty. He is the professor of the Department of Civil Engineering, Indian Institute of Technology, Madras. So before that, he was the he is the visiting professor, Department of Civil Engineering of IIT Hyderabad, and he has earned his degree, the bachelor's degree, from IIT Madras, master's also from IIT Madras in the year 1986, Doctor of Philosophy in 1992 from California Institute of Technology, USA. So his main research areas are nonlinear behavior of structures, displacement-based earthquake-resistant design of buildings and bridges. And he is involved with the seismic design codes. Honors and awards is the chairman, Earthquake Engineering Sectional Committee, CED 39 of BIS, a member, Second Advisory Committee, 2016 onwards on the National Disaster Management Authority, Government of India, 2016. Otherwise, also, he has a huge number of publications, which goes on 2 pages. With this, we just cut short his CV and now wait for our Director General, Mr. P.K. Mishra, to share his views. So over to Mr. P.K. Mishra.
Namaskar, Professor C.V.R. Murty. Namaskar once again, Professor Tandon, and all the respected guests who have joined this event. It's a matter of pride for us that Professor C.V.R. Murty has agreed to deliver this lecture on our Foundation Day celebration. In fact, our Foundation Day is on 26th of this month, but we preponed it, this event, as per the convenience of Professor Murty. This program, let me tell you, it is already more than 100 participants have participated, more than 480 have registered, and this is getting live streamed over YouTube right now. The streaming is going on. I'll be just taking 2 minutes time before Professor Murty takes over. I'll be talking about Institute for Steel Development and Growth, that is INSTAG. Many of you know about this institute, but I will still urge that you please visit our website to see what all activities we are doing. Because this is Institute of Steel Development and Growth, INSTAG is a very unique institute in the country. This is probably the only institute which is promoted by Government of India and steel producers to augment consumption of steel in the country, to find various ways and means how to augment usage of steel, mostly in construction areas. And that is what we are doing. This institute is about 28 years old, and it's a member-based institute, and we have got about 300 odd members, and many of them are distinguished, civil structural engineers. Our activity details are already given in the website. I request you to visit that. But we are basically doing a lot of training programs, a lot of workshops, conducting a lot of studies for imparting the knowledge of steel usage among the professionals. Because one of the findings in our institute is that the engineers who are perhaps probably coming out from tier 2, tier 3 colleges don't know much about the usage application of steel in construction. Most of them are taught about concrete. So when they come to the professional field, there is a dearth of knowledge about their application of steel in the workplace. That is where INSTAC is trying to, fill the gap. We have made a lot of training programs as per the requirements of these, professionals. We have also started a certificate course in collaboration with IAST Shibpur. It was a good success. The first program which we conducted in February, March this year, it was a good success. More than 60 professionals participated and they gave good feedbacks about the program. And we plan to launch some more certificate course in collaboration with other important reputed institutes. We are doing a lot of steel-based designs. In fact, 4-5 standard designs of rural structures like community halls, Anganwadi, we have already made in steel and they are already appearing in our websites. We have also made one standard design for road bridges because road bridges are not very common in India. So we have made a standard design of 30-meter span road bridge and with 6 different widths. And we have submitted that to Steel Ministry and Ministry of Murty with the idea that they should start using these standard designs and in case required, we can customize them. We are doing a life cycle cost study now because Government of India needs to be convinced that steel has to be, when in tendering stage, people have to consider steel as a material of construction. So that's the reason why we are trying to bring in the life cycle cost study, and with the help of IIT Bombay, we are doing that. And we are doing many other things also, like teaching resource materials. We have revised. Earlier it was made along with IIT Madras. Now we are revising it with the help of Professor Madhavan of IIT Hyderabad. We are doing quite a few, works in these areas. I would not like to go in details. I once again welcome all the participants to this program, and I request that in case if you like to associate with INSTAC or take interest in these activities, do write to us, do talk to us. We want to really promote this platform to be a very useful platform in the areas of augmenting usage of steel in construction in the country. Thank you.
I would now request Dr. Professor CVR Murty to start his lecture.
Thank you, Ghosh Saab. Good afternoon, ladies and gentlemen. I see a lot of senior colleagues, distinguished senior colleagues and friends in the list of participants, and I'm touched by their presence here today. Is the screen visible?
Yes, it
Yes,
is
sir.
visible.
Yes, sir.
Yes, sir.
It's visible.
Okay. So the subject here is a very wide canvas that we have chosen for today's discussion and lecture, the Foundation Day lecture. A journey from ductile steel to ductile steel buildings. And that is where we are bringing in a number of experiences that we have from the professional practice as well as from the academic work that we have been doing over the last 30 years or about 40 years. We're carefully watching the practice, how the practice is going, and we are also equally concerned, like Dr. Mishra Saab just mentioned, about the dwindling number of teachers in the subject of steel structures at the undergraduate level. It's a matter of serious concern, and while that remains, the practice is racing at a very fast pace. So today's discussion will focus around ductility, a subject that has been understood by some but misunderstood by many. And ductility will be discussed at 5 levels, and then we will close the discussion. But to begin with, I must say that 3 words that will be used rather regularly in today's 90 minutes is stiffness, strength, and deformability. Let's begin the discussion by looking at the applications. When you look at steel buildings, we have steel buildings that are low-rise commercials, even medium-rise residential buildings, and the very high-rise exotic signature buildings. In all of these, steel is has a center space in terms of making the structure feasible. But comes along with the excitement of feasibility is the fact that steel structures tend to be more flexible. And if you add glass to those steel structures, you will notice that this is going to be a recipe that we will need to worry about in the road ahead. So what are we going to discuss today? When you look at design, there are 6 aspects that you need to worry about. Strength, for which design forces are specified by standards. Serviceability, for which limits are specified by standards on how much deformation can happen. Durability, to make sure that steel doesn't corrode, and so on, how to protect it. And then robustness, integrity, and restorability are the 3 new items on the block, which you will start seeing to appear on the new Indian standards in the days ahead. Today's subject is not to talk about all 6 of them, but to talk about just the last 3, which involve ductility. And that is where you notice that ductility would come in once the structure goes into material nonlinear behavior. Then ductility will be the item of focus for us. In particular, we are talking about blast, fire, and earthquake as the backdrop of the demand on these structures. But today, I will use only one of them as a basis, understandably owing to the bias that I have had over the last 4 decades on the subject. When I look at earthquake resistant design, we have graduated from stiffness-based to strength-based in practice. And at the development of new standards, we are currently at deformation-based, and currently in research is the energy-based design. And when you look at the built environment, you will place them under normal, critical, special, and critical structures. And so the applicability of the older methods is on the lower level of structures and not for the important and critical level of structures. So the new, the critical and important structures will require more deeper understanding of the subject of steel structures if you really want them to survive without much damage in the next earthquake that we are going to see. So once again, deformation-based design is the word, and that will be the emphasis for us in the next 90 minutes. Earthquake-resistant design is special. That's because there's nobody pushing the structure, but there is a movement imposed at the base of the structure. That ground oscillation leads to relative deformation in the structure, and that is caused because of the presence of mass in the structure. And so inertial effects actually drive the deformations that are getting induced in the structure. It is important to know that there is a significant difference in the design philosophy for earthquake and wind effects. While earthquake shaking is a displacement load, wind is a force load. And so when you look at design, we are looking at under wind load, we are not expecting any damage to happen. The structure should more or less remain elastic. I might warn you here that in the road ahead, a lot of documents are getting populated in the internet, which talk about performance-based wind engineering, where under wind also they will allow damage. But I must recall a recent incident in Taiwan, where a tornado led to the sealant between the glass windows and the steel frame to go apart, and the water just came in. And for 3 nights, the entire population of those buildings were actually mopping their floors and getting the water out of their building. This is again because of the fact that steel structures are flexible. One, the sealants are brittle. Two, and the fact that the sealants have a finite life and you need to keep replacing them regularly over time. This is where on effects which are happening on a daily basis, we cannot afford the luxury of bringing in damage because the discomfort that the entire population in Hong Kong has been subjected to is unacceptable in terms of professional services being rendered by us. But when you look at earthquake shaking, there are different levels of shaking, and the damage will increase as the level of severity of the ground motion improves or increases. All that happens is the displacement demand increases. You would notice that we are not putting arrows from the vertical axis, but we are putting upward arrows from the horizontal axis, which is the deformation induced in the structure. This deformation will depend on the severity of shaking. I must also mention here that most standards worldwide today are only talking about what happens if you are far away from the fault region, and nobody is talking about the near fault effects in most documents. And this is where the trouble is, that 30% of India is sitting in the Himalayas. And so we need to make sure that we protect their lives and property in the road ahead. And so we need to make improvements in the estimates of deformations induced in structures in the Himalayas. So under small shaking or minor shaking that we call, which is regular, frequent, we should have no structural damage. Under moderate, some structural damage, and under severe, no collapse. But this is okay for normal buildings. For critical buildings like the hospitals and schools and so on, where we can't afford the luxury of structural damage to that level that the building cannot be used, we need to have a different philosophy. And that is what is slowly coming into the design standards. One of the items that comes into the play is actually the hazard level. You take a site and we know the maximum hazard that it can experience over a long period of time. It's a rare event, yes. So what happens is, even though it is rare, if you have to build dams or nuclear power plants, you don't take chances and use that itself for design. But if you are building critical structures, you will want to say, maybe I'll not use the entire one. I'll use a part of that hazard level for the purpose of design and allow a little bit of damage under this rare event that may happen. And instead of the full value, you will take a large fraction of that as a basis for design. In important structures, you will take more chances. And in normal structures, you will take a significant chance in terms of allowing damage in the structures. It is this reason that ductility increases as you go from the right-hand side to the left-hand side. In buildings, ductility demand increases, and also design has to now provide for that demand. And so we need to understand ductility a lot more carefully. So while I will define ductility a little later, we understand from the virtues, 7 virtues of earthquake resistant design, that there are 2 words or 2 properties of structures which are used interchangeably, and I want to have them not used interchangeably. And the 2 words are ductility at number 4 and deformability at number 5. We want to separate the 2, and we will show you why we need to separate the 2. When you look at the damage that is induced in the structure, we want to control the damage, and the damage should be of acceptable nature, and which means that we need large amount of inelastic response, but not lose so much of strength. But if we follow some of the older strategies for design, and if your structure has been designed by a very old code, you may be a little worried because that structure will perform like the red structure on this diagram, while today's standards may be pushing it to blue and in some cases to green also. So we need to see that if you have an older structure, we need to assess its performance. What is the important point? The point is that we are relying on the post-yield performance, and it's called the ductile performance or ductile response of the structure.